pleasant good morning to everyone present here. I'm Lena from Indian School at Seeb, and here we are going to be discussing Faraday's laws of electrolysis. And hopefully, by the end of the session, you'll be able to define and explain both of Faraday's laws and be able to solve numericals based on these laws. So before we begin discussing the laws of electrolysis, let's just brief about what we know about electrolysis. It is a process in which we bring about a chemical reaction with the help of electric current. And we conduct this process with the help of an experimental setup called an electrolytic cell. Let's take an example of a really simple electrolytic cell, which contains two electrodes, an anode and a cathode, which is connected to a circuit in the presence of an electrolyte. Let's suppose that the metal at anode is of impure copper, and during electrolysis, since it has negative electrode potential, it undergoes oxidation to release copper ions of +2 charge into the electrolyte and deposit on this electrode, and leaving impurities to settle down at the bottom of the solution, giving us really high quality copper. What do we understand from this example? So from here, the question here is, how much copper do you think will be deposited on this electrode? And during 1830s, a scientist named Faraday had a similar question. And during his extensive research on the topic of electrolysis, he found that there are three factors which affect the deposition of metal on an electrode, which is the quantity of current passed through the electrolyte, the time in which it has been passed for, and the charge on the ions which are being deposited. And based on these three observations, he gave two laws. The first law states that the amount of chemical reaction which occurs at any electrode during electrolysis by a current is directly proportional to the quantity of electric charge passed through the electrolyte, which means that the mass of element which is deposited on an electrode is directly proportional to the charge passed through the electrolyte. We can write this in the form of current as I dot T, as we know that current is nothing but charge per unit time. And we can remove this proportionality symbol by just using a proportionality constant called the electrochemical equivalent. We can define this electrochemical equivalent as the amount of the substance deposited or liberated when 1 coulomb of charge is passed through an electrolyte. But the thing is, we often calculate this value experimentally, but for our convenience, we can just, for instance, we can look at the definition, we can write it mathematically as equivalent weight when one coulomb of charge is passed. So before we discuss more about the ECE, we can just look at this electrolytic cell where the deposition of metal is actually happening, where the reduction is happening. We can just write it as when one mole of copper ions get reduced to 1 mole of copper with the help of 2 moles of electrons. So what is the equivalent weight we get on this electrode? To calculate that, we know that electrolytic weight is equal to molar mass divided by the number of electron transfer. The molar mass of copper is 63.5 grams divided by 2 electrons. So with that we get 31.95 grams. But we know that during electron transfer, we are not just transferring electrons, we are also transferring charge. So since we are talking about moles of electrons and moles of ions and copper, how many moles do you think charge do you think 1 mole of electron has? We can just calculate that as Avogadro's number into charge of 1 electron, which is 1.6 to 10 raised to minus 19, which will give us the number as 96,487 coulombs. And for calculation purposes, we can just round it off as 96,500 coulombs, which is known as, this number is a constant known as the Faraday's constant. So if you're going to substitute these values over here, we can just write electron as the molar mass, equivalent weight as molar mass divided by the electron into the Faraday's constant. And substituting this value over here, we can just get as I hope this was pretty clear to you. This is what basically we derive from the first law. Now moving on to the second law. It states that the amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to the equivalent weights. What do they mean by this statement? So let's suppose we have two electrolytic cells where we are passing the same quantity of electricity between two of the cells. And it says that the ratio of their weight deposited will be equal to the ratio of their equivalent weights. Let's understand this using an example. We have three electrolytic cells here which contains silver nitrate, copper sulfate and aluminum nitrate. And the ions transferred here are silver ions, copper ions and aluminum ions. And if you take the ratio of their equivalent weights, we know the molar mass of silver is 108 with 1 electron divided by 1 electron, and molar mass of copper is 63.5 divided by 2. And the molar mass of aluminium is 37, which gives us 9. The ratio of the examples that we took where 0.8 is to 9, and this exact same ratio is the ratio of their weight deposited, which is what basically we are learning in the second law. That ends our discussion about the electrolysis, the laws of electrolysis. But before we conclude our session, I just want everyone to do a numerical for a minute and try to solve it. 3 electrolytic cells A, B, C containing solutions of zinc sulfate, silver nitrate and copper sulfate respectively are connected in series. A steady current of 1.5 amperes was passed through them until 1.45 grams of silver deposited at cathode of cell B. How long did the current flow for? What is the mass of copper and zinc which were deposited? I guess I can show you the solution. Is it fine? To approach this question, we can just say that the 108 grams of silver were deposited by 1 Faraday. So to calculate how much 1.5 grams of silver deposited, we can just say that. So to calculate how much 1.45 grams of silver were deposited, we can just say that 1 gram of silver deposited is 45 into divided by 108 into 1.45. Do you understand how I got this? Yeah. And since the answer we are going to get is 1295.6 coulombs. And to calculate time, we can just substitute in the equation called charge is equal to IGT, and we will get our answer as 863 seconds. And for the mass deposited at cell A, we take the same approach. So to get 2F, so to get 5 grams into 2 into 9650 into our desired value, which is we will get the answer as 0.438 grams. I just want everyone to understand how we approach this question. Understand? In the same manner, we are going to approach the third section of this column, of this question. I just want everyone to understand. Is everyone understood? You have to approach the question? Yeah. Next is an MCQ questions. So whoever knows the answers, please try to answer the question. In the electrolysis of aqueous sodium chloride solution, which of the half cell reaction will occur at anode? Yeah, I say it's right. The correct answer is option A. Since it has negative electrode potential, the oxidation always undergoes at anode. So since it has negative electrode potential, we can just say that the reaction which occurs is option A. The quantity of charge required to obtain 1 mole of aluminium from aluminium oxide is?
3F.
Yeah, I just said it. Since the valency of aluminium is 3, the answer is 3F. That's it for my session. I'll be taking the doubts for now. Why does anode have negative electrode potential? Since it undergoes oxidation more easily than the H plus ions in solution. That's why it has negative electrode potential. Since it requires us for the ions to be free, it have to be an electrolyte. So it has to be, to disassociate really it has to be some aqueous solutions. It can be industrial applications that we stated that it gives us high quality copper over here in this example. So it can be used for application for industrial purposes as well. That's the only application we are learning today. But there can be more applications as well. It means that how much weight is deposited when how much weight is deposited for 1 electron or 2 electrons. Can you repeat?
Can you explain the movement of
Ions. The ion, see, over here during anode this undergoes oxidation, which means that since you have copper over here, it will undergo oxidation to give. So since this dissolves at anode and releases copper, it goes deposits on here to reduce and give us copper. If you are talking about how we got positive and negative electrons, we can just say that it all depends on the electron potential. Like, was that what you're asking? Is it out clear?